Hi guys, let's look at the Thermodynamics and Kinetics handout. The importance of these two topics can be illustrated with these two reactions here. If we take nitrogen trifluoride, it undergoes a decomposition reaction to nitrogen gas and fluorine gas. Same thing with nitrogen triiodide, nitrogen gas and iodine. These reactions are balanced. One of the rare times you'll ever see me balance a reaction. It does need to be balanced for the purpose of calculations that we will be doing. Types of questions that could be asked for these reactions. Which of these reactions will give off the most heat? That is energy, heat energy. Which reaction of the two above is endothermic? Which reaction will occur fastest? Now the first two questions are thermodynamic in nature, while the third one is more rate related, fastest. We can also ask, are the reactions above driven by entropy or not? So these are the types of questions that you should be able to answer. Hopefully you looked at such type questions in Gen Chem. As we move forward and look at more alkene reactions, we'll ask very similar questions. As we move forward again. So it's very important to review this type of material and thus be prepared for what we're going to see moving ahead. Okay, I can add a few more things here. We'll proceed. This is really a warm-up page. You can come back and work this after we go through this a little bit. The first question, here's your chance to use your calculator. And such questions will largely be, you'll need to use bond strengths. And here's a table down here of bond strengths. You'll need to use bond strengths to do such calculations. Okay, let's look through this handout. First thing we need to look at is to make sure we're familiar with so-called line reactions. A line reaction shows a reaction. It shows reactants on the left side, then a reaction arrow, or what looks like a line maybe, and then product or products. It can be shown like this. This alkene plus HBr yields, and the reaction arrow pretty much means yields this product. Sometimes we can put some of the reagents or reactants on the reaction arrow, and so the same reaction could be shown like this. This is very common instead of showing it with a plus up above. Also, we can show conditions on the reaction arrow or reaction line. The alkene reacting with HBr at 25 degrees Celsius for 1 hour. That would be the reaction time to yield this alkyl bromide. Note that a single line reaction may also show multiple steps. Really, this is two different line reactions really combined, but this is commonly done. You might even see 1, 2, 3. Whenever you see the 1 and 2, you have to keep these separate. The alkene is first reacted with HBr. Okay? Ignore the 2. That is not included. After reaction with HBr, you have some type of product. That product is then reacted with sodium cyanide in a second separate reaction to give the product shown. Common mistake students make here is that they believe, or you guys believe, that all this is there together at the same time. No. Separate. HBr is the first reaction. We then purify a product, usually. Then we come back and react an intermediate product with the next reactant. Okay, so that's examples of line reactions. All right, thermodynamics. Mainly review. I've sort of reviewed it a little bit. This should be straight from Gen Chem. Equilibrium, products over reactants, concentrations, etc., etc. I'm not going to read this to you. We can boil this down to take-home message at the bottom. Gibbs free energy equation, delta G equals delta H minus T delta S. Where delta H is your enthalpy or heat energy, and delta S is your entropy. Of course, temperature is in this equation. And hopefully you have a sense of what this equation is used for, what information it can tell you about your reaction. Okay, we said delta H is the heat energy. Now, this directly relates to bond strength. And on the first page, we saw a table of bond strengths. All right, and that's where we're going to be doing calculations of using those bond strengths to determine our delta H. Things we can remember here. A positive delta H, that means products have gained heat energy. Negative delta H means the products have lost heat energy. Positive delta H would be endothermic. Negative delta H would be exothermic. Exothermic is a more favorable outcome. And we would say, if this was the case, we would say the reaction is thermodynamically driven or thermodynamically favorable, where thermodynamics largely refers to the delta H. Entropy. Entropy is the randomness or disorder that's in a reaction. And the entropy is the change in that disorder. Positive entropy, positive delta S, products have gained disorder. That's favorable. Nature wants to become more disordered. It likes to gain disorder. This is sort of like a double negative, or we could say the products are less ordered. That'd be the same as gaining disorder. A negative delta S is where the products have lost disorder. That's definitely a double negative. Lost disorder. That means they have gained order. If the reaction has gained order, it's a negative delta S, and that's not favorable. Just like if you drop a coffee mug, it's going to shatter into a number of pieces. It's going to gain disorder. You're never going to see all those pieces sort of randomly come back together. Okay, so we need to know which of these is favorable. And what type of reaction is driven by enthalpy or thermodynamics, and what type of reaction is driven by entropy. All right, let's look at some examples of entropy. Delta S. In this reaction, this alkene, which by the way, nomenclature, very important. There will be a video on nomenclature. This alkene would be 2-propene. I'm sorry, 1-propene. No such thing as 2-propene. 1-propene, yeah. Actually don't need the 1 because there's no such thing as 2. So it's just propene is sufficient. Okay, propene plus HBr yields this alkyl bromide. This is 2-bromopropane. This reaction would be expected to have a negative entropy. Delta S would be negative. Why? Because what's going on here? 2 molecules are reacting to give 1 molecule. The 2 molecules are coming together. The molecules are now ordered, more ordered. They have to come together and 2 become 1. That's a more ordered. That means the molecules, the system has lost disorder. Lost disorder would be a negative delta S. And indeed, that's what we said. Let's consider the reverse reaction. If the alkyl bromide went back and decomposed into the alkene and HBr. I'm showing that reverse reaction here in the forward direction. The alkyl bromide decomposes into the alkene plus HBr. Here, delta S would be positive because the system has gained disorder. 1 molecule went to 2. It became more disordered. The system has gained disorder. So, which reaction, A or B, is favored by entropy? That would be reaction B, because it's becoming more disordered. Okay, so here we went from 2 to 1 and we went from 1 to 2. Okay, pretty straightforward approach to assessing delta S. How about C, reaction C? Here, this 1 molecule forms a ring. The oxygen becomes bonded here. 1 molecule becomes 1 molecule. How do you judge entropy here? Well, what's going on here is this molecule has to become more ordered when it becomes a ring. In the open chain form, all of these bonds have free rotation. And there's lots of rotation possible here. And that's part of the randomness that's built into this molecule. When the bond is made to make the ring, it really restricts the rotation that you can do in some of these bonds. The restricted rotation decreases the randomness, and the system has thus lost randomness or lost disorder. Thus, delta S should be negative. So that's another way to judge delta S. Okay, delta H. Again, delta H is where we're going to do calculations. Delta H is easier to quantify. The delta S we're not going to quantify. We're just going to qualitatively assess it in the manners in which we did up here. Delta H we can quantify. And we can look at it particularly by looking at bond strengths. Let's look at this reaction here. This alkene reacting with HBr, it's quite similar to up here except I've removed a methyl. Up here we have a methyl. Here we just have ethene, slang name known as ethylene, plus HBr yields the alkyl bromide. Let's do a delta H calculation. To do this, we need to look at what bonds are broken in this reaction. The carbon-carbon pi bond is broken. It's no longer in the product. What is the bond strength for a carbon-carbon pi bond? I would say we can look on the front page But this table doesn't show carbon-carbon pi bond. It shows this here. We have to be careful though. That's for the entire bonding between the two carbons. That's the pi and the sigma. That's not clear, but I'm telling you that. Over here, this value is for just the pi bond. Again, I would have to just tell you that. And that's kcal per mole. That bond is broken because we no longer see it. What other bonds are broken on this side? Right here, the HBr bond is broken because it's no longer there. How strong is the HBr bond? We can look on this table and see if it's there. HBr. The bond strength is 87 kcal per mole. That's where that 87 came from. The two bonds that are broken add up to 150 kcal per mole. We need to look at what bonds are formed. Carbon-bromine bond is formed. But we can distinguish what type of carbon is this. It's a primary carbon because that carbon is bonded to just one other. Because often tables will have different types of bonds depending on if the carbon involved is primary, secondary, or tertiary, etc. This is a carbon-bromine and the carbon is primary. Let's see if that's on the front page. Right here. Carbon-bromine, the carbon is primary. It says 72 kcal per mole. And we see a difference. Okay. Some tables will give you a different value. My value of 69 came from a different table. All right. Don't let that confuse you. If we had used this table, we would have used 72. I put 69. What other bonds are new? We made a new CH bond. And this is a primary CH bond because the carbon is primary. Okay, here. Let's see if that's over here. Primary CH, right here. 101 kcal per mole. Indeed, that number is the same here. We can add these up and we have 170. So, the strength of the bonds that were broken, 150 kcal per mole. The strength of the bonds that were formed, 170. These bonds are stronger. Okay? Because these are bond strengths. Higher number, stronger bonds. This is actually the energy it takes to break the bond. Bond strength. It takes more energy to break these bonds. The bonds we made are stronger. Stronger bonds are more stable. More stable bonds thus lower in energy. The system is now lower in energy. Since the system is lower in energy, this reaction is exothermic. What is delta H? Delta H is negative. It's exothermic. Negative what? 20. Difference in the two. Units, kcal per mole. So delta H is negative 20 kcal per mole. It's exothermic. We see that because we made stronger bonds. Stronger bonds should be lower in energy. This side is lower energy than this side. You can't just go to lower energy and let the other energy disappear. The other energy comes out. So we actually create 20 kcal per mole. Heat is released. Since heat is released, we say delta H is negative. Okay. So, in terms of enthalpy, this reaction would be favored because delta H is negative. But based on entropy, the reaction is not favored because two molecules are reacting to become one, more ordered. All right, how did I know this was going to be negative 20 and not positive 20? Well, I explained that. Now, you may have just sort of memorized that you subtract one from the other. Which one is that? 150 products minus what is that? Reactants minus products minus 20? Yeah, you can do that, or you can understand what I just discussed over here if you want the full explanation. Got to be careful about just memorizing math because if you're asked to explain any of this, you're going to have a tough time doing it if you don't understand it. Okay, so that reaction is exothermic. What about T delta S? I told you reaction is not favored based on entropy. Okay, what about delta G overall? Because look, for this reaction we just did, delta H is favorable, but delta S is not favorable. So what about delta G? That can be difficult to tell sometimes. We didn't quantify delta S. We're never really going to answer delta G overall. We're going to focus in on delta H and make a qualitative assessment of delta S. One thing's important though is T magnifies delta S. As you learned in Gen Chem, right? Temperature magnifies your entropy term, yeah? So, we could ask a question here. Would heating this reaction help it? The answer to that is no. It's not favored by entropy. The entropy term is bad here. Since the entropy term is bad, you would not want to heat it because temperature magnifies entropy, and if entropy is bad, you don't want to magnify that bad term. Hopefully that makes sense. Again, hopefully that sounds like discussion you had in Gen Chem of how temperature influences reactions and how you can see it in your Gibbs free energy equation. Okay. Here's some practice you can do. Calculate delta H for reaction for the following reaction. Tell if the reaction is exothermic or endothermic, if it's favored or disfavored by enthalpy. Here we have an alkane reacting with fluorine, elemental fluorine gas. We're doing a fluorination at the tertiary carbon, producing HF. This is completely balanced, 1, 1, 1, 1. And in terms of mechanism, it's a radical fluorination. We'll look at this type of mechanism near the very end of the course. There's other questions we could try to answer here. I want to compare the delta H and the delta S to the previous example being the one over here. Then I want you to repeat these calculations using iodine here instead of fluorine. And consider the differences in the reaction when iodine is used. And then explain why the big difference in the two reactions. You'll see a big difference in your calculation when you use iodine. Why the big difference? Okay, let's look at kinetics. Kinetics, of course, describes the rate or speed of a reaction. Largely depends on the activation energy required for a reaction. Activation energy, of course, must be overcome for a reaction to occur. Okay, we need to become familiar with and be able to use reaction coordinate diagrams. Okay? These diagrams are going to show the progress of the reaction, where you start with reactants and end up with products. It may be a complete reaction, or it may just be a partial reaction. So on the x-axis, progress of the reaction. On the y-axis, some type of energy, free energy. It can be maybe shown as free energy, delta H or delta G. It doesn't have to be that specific for us. I will largely refer to delta H because that's what we can more specifically calculate. But in some of these examples, they may show delta G. Okay, here we see reactants going to products, and it just looks like there's no intermediate. There's just one transition state. And this would be the activation energy. And this would be just one transition state. The entire thing here is a transition state, but this is the highest energy of the transition state. This is transitioning sort of towards products, and it gets like, I would say maybe halfway there, but that's not correct. But from here it starts looking more and more like products until it becomes products. Transition state, also called the sometimes activated complex. Transition state is where you have bonds forming and breaking both at the same time. It's a high energy species. Not an intermediate though. It's not a discrete intermediate. Okay, in this reaction we have an activation energy with one transition state leading to products. It looks like an exothermic reaction. Delta G is negative. Where in this example we have a transition state and activation energy leading to products, but this would be endothermic. Or if you're using delta G, more precisely, would be to say it's endorgonic. I will typically just say endothermic because usually I'm referring to delta H again. Okay, so of these two reactions, which one is most favorable or so-called spontaneous? You got to be careful what spontaneous means. Typically, for me, that's a thermodynamic term. It's exothermic. This one is more favorable, naturally favorable. Negative delta G or negative delta H. Okay, let's look at these diagrams here in the middle. We can ask some questions. Which reaction is most favorable of these four? Well, it would be the top two, right? Because they're both exothermic. The bottom two are both endothermic. Which reaction, though, is most favorable? A little bit hard to see, but this one appears to be most exothermic. The line's a little longer. The distance is more exothermic than that. A little close to tell, but that one is more exothermic. So which is most favorable? I would say B. But which reaction is going to be fastest? Hold on now. It says which favorable reaction is fastest. A and B are both favorable. Which of A and B is fastest? That would be A. So that one's B, but the fastest is going to be A. Why? Because A has the lowest activation energy of the two. It's easier to get over that energy barrier than this reaction here. The exothermic nature really doesn't matter when we're talking about rate. Rate is based on activation energy that must be overcome. This is the reason why diamonds do not explode in oxygen. The combustion of a diamond is very exothermic reaction, very favorable thermodynamically, but it doesn't occur with any appreciable rate because the activation energy is so high, it turns out, for that reaction. Okay, let's look down below. This reaction coordinate diagram shows an intermediate. All right, you have this energy well. It's an alkene reacting with HBr. We have a transition state leading to an intermediate. And then from there, and this is the intermediate, okay? The intermediate is this carbocation. And it has a certain energy. Typically we'll draw it like that. That's an energy well. From there, the intermediate then undergoes a second step, and maybe you can call these two steps elementary steps. A second elementary step in the reaction mechanism to produce the final product. And that step has a transition state. So you have a transition state leading from here to the final product. So two transition states, one intermediate. What is the rate determining step? Two different steps. Which one is rate determining? Rate determining step is going to be the one with the greatest activation energy. And that would be the first one. That would be your rate determining step, is formation of the carbocation intermediate. And the second step would be simply called a fast step. That's just relative to the slow rate determining step. All right, and this reaction is overall exothermic. Very similar to how this alkene reaction here was exothermic. Okay, reaction coordinate diagram here shows two different reactions. No, I'm sorry, not two different reactions. It shows this reaction. It shows two possible intermediates. Okay. So we're starting here with the alkene, we'll call that A. two possible reaction pathways to lead to two different intermediates. And these intermediates each have different energy. Here they are. This cation, it's a primary cation. And this one is a tertiary cation. That is, the charge is on a primary carbon. Here the charge is on tertiary carbon. The charge on the tertiary carbon is going to be more stable. We should know why. Because this carbon has 3 rich friends inductively donating electrons, where this carbocation only has 1 rich friend, 1 chain of induction versus 3. When it's branched, it's like 3. More inductive donation, more stabilizing of the positive charge. Makes it more stable, lower in energy. Importantly, what we usually assume here is that the transition state leading to a lower energy intermediate is going to be lower in energy itself. And that's what this shows. At the same time, the transition state leading to a higher energy intermediate is going to be higher itself. This is a normal assumption we make. Sometimes we can be wrong, but this is our starting assumption. This sort of comes from the Hammond postulate. Now this is only showing formation of the intermediate. From here we can continue on. Really it's just showing the first elementary step here, but it's showing the idea of having two different intermediates that are possible. Now a question that we could ask over here is, let's call this one B and this one C. And thus, this is B and this is C. Which intermediate is most likely to be formed? Hopefully that's pretty obvious. The answer is C. Why? You might say because it's lower in energy. Well, sort of that's the answer. But really the answer is over here. C is formed because the transition state energy or the activation energy leading to it is lower than the activation energy leading to B. All right? So we really need to look here. But again, if we assume this assumption we made is that the activation energy for B is going to be higher. But make sure you understand what you're discussing here. The energy of this versus the activation energy of the transition state. Okay, this reaction coordinate diagram here shows one reaction going to a common intermediate. But in this case, from here, 2 different possible products. Where up here it was 2 different possible intermediates. And here we have an exception because, first off, this reaction gives 2 products. One is called a 1,4 product and one is called a 1,2 product. Now, which is more stable? Clearly the 1,4 product is more stable. You can tell that from here. But could you have told that from looking at the structures? Let's draw a line bond here. This is a boom, boom. This doesn't show cis or trans. I'm going to make it trans. There's that product. This product is that there. 1, 2, 3, 4, 1, 2, 3, 4. Yes. It's easier for me to look at line bond structures because I get confused. You got to look at this close. Where are these H's attached? That's an alkene, carbon. Okay. One carbon has an H, the other methyl carbon has an H, then the CH2Br. It's easier for me to look at line bond structures, and we see that this is a mono-substituted alkene, this is a di-substituted alkene, and as we'll see in the nomenclature video, these are isomers, constitutional isomers. The di-substituted alkene is most stable. Now the 1,2 versus 1,4, don't worry about that now. We'll cover that terminology during test 3 when we actually look at this reaction in more detail. Okay, for now we know one is more stable than the other. We usually assume that the lower energy intermediate or product has the lower transition state leading to it. But in this case, that is not true. This is an exception to the Hammond postulate. The transition state for the 1,4 product is actually higher. Questions we could ask here. From here, which product is going to be formed fastest? And the reaction would be the 1,2 product would be formed fastest. Fastest is going to equate with easiest, right? The easier one's going to be faster, right? Which one's easier? Lower energy pathway. The lower energy pathway, though, leads to the 1,2 product. It turns out it's the less stable of the two products. The 1,2 products form fastest and is thus called the kinetic product. Okay? Which one of the two products is most stable, though? Well, that's the 1,4 product, and it's called the thermodynamic product. It's not formed fastest, though. Now, I'll give you a little prelude to this down the road. If we do this reaction cold, you get the kinetic product. If you do it warm, you get the thermodynamic product, because if you do it warm, equilibrium occurs. And if you can establish equilibrium, which one's favored then? The thermodynamic product. If equilibrium is not established, you just get the one that's formed fastest, and that would be the kinetic product. Lots of good information here. But to understand all this information, you have to understand this handout, and particularly reaction coordinate diagrams. Okay, let's look below here. This last one is just showing one transition state. That's really like was over here. They're not showing any difference between the energy of the reactants and products. Just showing a transition state. This looks like an SN2 reaction. We'll look at that during test 3. I reckon a question we can ask here is, how can you increase the rate of this reaction? Or any reaction? I mean, up here we were doing two different outcomes. This is sort of getting ahead a little bit. You can refer back to this along the way, but if we can lower the transition state energy, for example, if we can, same reaction, if we can somehow bring this down, lower that down somehow, That's going to make the reaction faster. It's going to increase the reaction rate. What are ways we can bring this down? Now, the traditional answer to this question is, well, include a catalyst, and a catalyst lowers the transition state energy. Yes, it does. But there'll be many other ways we can do it, but we may not be doing the same reaction, though. But we may start comparing two different reactions, and we can say, well, this one's got a lower and it's going to be faster. At that point, though, we're really doing what we did up here. Which is going to be formed faster, B or C? Well, C, because it's got a lower transition state. But we really need to understand why. Okay? So I reckon I felt like we just needed to show this type of reaction coordinate diagram again. And again, this handout is going to be for reference moving forward. Okay. So we can come back to the front, and hopefully you're able to answer these questions now. Okay, two example reactions up here. Which will give off the most heat? All right. Or most energy. How did we do that? Remember, here's your chance to use your calculator. Bond street tables. A bond street table is here. Which reaction is endothermic? Well, that's probably going to come from just looking at your results from number 1. Which reaction will occur fastest? Okay. You might have to think about it. You could always do a quick reaction coordinate diagram to help gather your thoughts. Okay. Start getting something on paper and looking at the reaction progress. You might want to focus in on the rate determining step, because the rate determining step is the one that determines the rate. Are the reactions driven by entropy or not? We did a couple of examples of that. Okay, so a little warm up. By the way, bond strengths that are needed for these reactions are not down here in the table, but instead I gave them here for you. And in this case I gave kilojoules per mole. Where I may have been working with kcal per mole within. Okay guys, that's an overview of this handout. Let's see what type of questions come up. And we will certainly use these ideas, and we'll be drawing reaction coordinate diagrams for each reaction that we do. You'll be expected to draw them in things like lab reports. Very useful. Sort of like when I introduced the doing hybridization diagrams, energy diagrams. Very useful for organizing your thoughts. Okay. Getting something on paper. Then you can just be thinking deeper about what's going on, and you are able to ask better questions, etc. Okay guys, we'll end that here for this handout.